trend, we have Tom Bending to talk about Phantom on GPUs with OpenMP. Take it away.
Thank you. So a very similar theme to our previous talk. Yeah, so I'm Tom. I'm from University of Exeter, and I'm a postdoc working with Matthew Bate. So my background has been using SPH for star formation, stellar feedback, the interstellar medium, and the initial MASH function mostly. And throughout the time I've been involved with all of this, I've been using mainly SPH-NG, predominantly for the MPI, and because it's got photoionization routines in it from when I started back in 2016. They just arrived. It was the right time, and I've kind of got stuck there. Just become too reliant on the things I know. Over all this time, I've become increasingly focused on code development and optimizing SPH-NG and the MPI within SPH-NG. And most recently, I've been getting interested in GPUs. But yeah, I'm going to move on from, I'm not going to talk about my science at all because yeah, much larger scales than any of you are really interested in, apart from so far from what I've gathered, maybe Cheryl, but even then. But yeah. Okay, so I started a GPU project. I've had it in my mind to do some stuff with GPUs for a while. When I started my postdoc with Matthew, I know he's always been interested in me exploring certain things to do with GPUs, mainly some of the radiative transfer and dust that he's put into SPH-NG recently. I should mention, for those of you that aren't aware, SPH-NG was started, I believe it was started by Willy Benz in the 80s, and then Matthew took it over. And it's kind of a progenitor to Phantom in many ways. I know Daniel mentioned some of the weird idiosyncrasies come from SPH-NG, but it's not publicly available and it's not very widely used. Okay, so I started the GPU project because the dust stuff I just mentioned and some radiative transfer is just way outweighing the hydro. And those are both things we can offload to GPUs reasonably easily, we think. Whereas trying to attempt to do the hydro in SPH-NG with GPUs is too intimidating a task, I think, because of the nature of the tree structure and many other things, with it being an older code. So I 3 months ago started writing just a simple density solve with the idea of making sure that as much memory could be aligned as possible in particles. So I used a Morton ordered octree to do that, which gives you chunks of particles that are all in a grid cell together. And then you know that they're always going to be aligned in memory, which allows you to use vectorization and hence get up to 8 calculations at once. So it's a theoretical speed up of 8 if you're working on a system that allows that. Most systems probably give you a factor of 4 with vectorization. AMD systems typically, although the most latest allow 8 as well. Intel systems more often 8. The method I've used completely avoids neighbor searches and neighbor lists outside of the tree build itself. So once you've built the tree, you know exactly where you're going through the walk, and you don't have to worry about any of that. And all of the summations of neighbors are vectorized. So I'll show you how it's achieved in this particular case. So some of you will be familiar with this. I'm sure lots of you maybe aren't. So apologies if I go through it slowly. So it's an octree, here represented as a 2-dimensional quad tree. So we break our domain up into cells. So here is one quad, another, and then you can imagine another cell with a division like this. So we just get smaller and smaller and smaller, but we order it with this Z order. Okay, and that's the key. And we can then turn a 2-integer set of indices for our particular cell in the tree into a linear array by using bit interleaving. So we take the 2 bits that represent the X and Y coordinates and interleave them like this, and we get, this is the 0th cell, the first, the second, and as we go on. Oh, sorry, the second, the third, the fourth, the fifth. And then we sort our particles so that they follow this alignment. So the particles have to be sorted quite frequently, but so far that doesn't seem to be too much of a problem. Because initially it's quite a big expense because they're all out of order, but once they're in order, the order isn't changing very much. So it's just a few particles you need to move to keep the order going nicely. Now, the big advantage of this comes if we ensure that we know that all of the neighbors of the particles in cell 3 are going to be found in a neighboring cell. And that means the walk is really, really easy. So what do we have? Again, and because all the particles in each of these cells are contiguous, we don't need to keep a list of all the particles in the cell. We just need to keep the first and the last. And then, in fact, when I build the tree walk, I don't need to keep the first and the last, because I know that these all need to be checked up to here. So I just take the first of this and the last of this, and I've got a nice big chunk of contiguous particles, which is great for the GPU. I might even choose, if there's a small enough number of particles in this cell, for example, I might even choose just to add those and then keep and calculate them, even though it's pointless, they're unneeded. And the same here, all the way up to here. So that's one contiguous chunk. If I include these, maybe there's only a few particles in each, and then probably exclude these maybe, and then just one other cell to do. So we suddenly got massively aligned memory. And maybe naively, I don't know too much about GPUs before I started. I started learning about GPUs 6 months ago. Mostly I've been interested, but not really understood anything for a year or so. I've assumed that achieving all of this memory contiguity is the way forward. And so that's why I built this purely for vectorization first. And this is, having built the tree walk, this is the number of contiguous J particles in a particular walk. So in other words, that and then this, I didn't include these, haven't included these, this, then these, and then this for every single I cell. And so this is one particle happens 12 times, and we get many thousands of particles 100 times, and most of these regions, as we'd expect, are of the order of 50 particles. Yeah. Okay, so that's a real step forwards. Okay, then after having done this, I was still all on CPUs at this stage. Was it in April? I went to the Dirac AMD hackathon in UCL with Beck and Adam Cavall from Edinburgh. And we ported the code to GPUs, and we ran it on an AMD MI300A. We made a lot of progress there, and then soon afterwards we had it up and running, and we got some speed up, which I can show you here. So this is one of AMD's flagship GPUs. Well, they actually call it an APU and an accelerated processing unit. It's all integrated. It's got CPUs and GPUs on the same chip with completely shared memory. So there's no offloading in this case, and it's got 196 cores and 4 GPUs all on this. So it's a huge, absolute beast of kit. And then we get perfect scaling up to 24 cores, and then probably some memory issues beyond that. They might have the other 24 cores maybe aren't in the same socket or something like that. I'm not entirely sure of the geometry. We dropped off. But compared to running on 48 cores, we're nearly 5 times faster on the AMD, which is great. The next step in my project was to integrate my CPU code into Phantom. So I've run now on Phantom, and what I did was build both trees, my tree and Phantom's tree, and then I did the density solve with the CPU version of my code, the vectorized the code, and we got basically comparable speed, tiny bit faster with my code. The reason for this is that to do it our way, the labor lists are quite long, because you have to calculate all the summations over density for every single potential neighbor, rather than identifying which are potential neighbors and then doing that. So that's about 5 times more work. But because we're not doing any tree walking and we can use vectorization, we come out in the long run a bit faster. And hopefully, as we see with the GPU, a good chunk faster again. Then most recently, I got the code working on an NVIDIA system, so that's with offloading. And in that case, on a completely different node, I had the code running 2 times faster than the 24 cores on that node. And the times faster than the NVIDIA, but that is expected. You'd actually expect, in terms of the teraflops, the trillions of particles, trillions of floating point calculations per second, of floating point 64 calculations that these can do. The AMD chip should be 6 times faster than NVIDIA, but it's only 5 times faster. That shows that the code probably is running a little bit better on this, even though it's a much slower chip. Okay, so this week, if any of you have access to GPUs and are interested in trying it, I'd love to try and run my code on a new GPU that I haven't run it on yet. I want to talk about MPI strategies for my code. I'm not planning to do anything with MPI in the near future, but I want to know what my long-term MPI strategy is. So discussions with any of you that are interested in these things would be really helpful. My GPU density solve can't yet do iterations, so I just need to work on that and maybe get that done this week. Also, handling neighbors that are outside the zone of compact support is difficult. So for solving density, you only need to find the I particles neighbors. You don't need to worry if that particle is also a J particle neighbor and hence therefore a neighbor for force and gravity calculations. But for finding density, I don't need to worry about that. So that's an extra complication.
Sorry, that's me. One second.
There we go. Okay. And I'm hoping that once I fix this, I will also be able to this week implement the GPU density solve in Phantom and see how that works. So that'd be great. And most importantly is to find collaborators. And it's been so fantastic to learn about Andy, because I really don't know what I'm talking about with GPUs, and but I've got a lot of experience in SPH, and it seems like Andy is from his background. I'm really excited to talk to him because he seems to know an awful lot about computer science and this type of thing. So, thank you very much.
Have any questions for Tom? I'll ask the question. I think you said, I know. Do I need the microphone in the front? I'm not sure. Find out. My question was, you said a moment ago with the A100, it was about twice as fast as 24 CPU cores. But most nodes, I could get 48 cores quite easily.
Yeah.
And presumably go twice as fast that way. So what benefit does the GPU add if I could just use the available cores in a shared memory environment already?
It's a very fair point. In that case, we'd get about parity if there were 48 cores available. The thing I'll add is that this is all very early stages. There's a lot of optimization still that I think we can do. There's also things that are going to make life more complicated, and things for doing force, it's going to be slower. So yeah, it's a very fair point.
Yeah, I'll follow up my question with can you go into a hybrid scenario? Are you thinking about a hybrid scenario?
Absolutely thinking about a hybrid scenario. Yes, I mean, I would want to be using CPU cores to do other things. I would, although I've been warned about caveats in the pub last night about that. But yeah, in an ideal world, if it works, we'd love to be doing work on CPUs while also using GPUs. Yeah.
Cool. Yeah. Yeah.
For the comparison test, did you check the power in terms of watts? In terms of, did you make sure that the energy power you require for the test is in both cases? Did you do the test at the same energy consumption?
Did you get the question?
I think I got the question. So the question is, does using the GPUs use more energy or less energy than CPUs?
Yeah, what? Like, it's at the fixed number of watts of power.
Yeah, so I think at the moment the GPU, well, I believe that the power consumption of GPUs is on average. So if you put a GPU into a node, you double the power consumption of the node.
in your case.
I think that's a general.
What was the CPU model you had? I can tell
For
you.
the A100, I've got no idea, but for the MI300A, it's all integrated into the one APU. It's all so they're always exactly the same. But from speaking to people about these things, as I understand it, it's a very vague rule of thumb that by putting in the GPU, you double the power consumption of the whole node.
My point is, when you compare GPU to CPU, you check that in both tests, the power consumption is the same. You see, you run tests with GPU, you are using, I don't know, hundreds of watts. For the CPU, do you have the same number of watts when you perform the test?
How do you make a fair comparison?
Yeah.
One way to make a fair comparison is to put them on the same power consumption.
You
You're saying even if you run the same speed, it's using a lot less electricity.
Yeah.
You're on the MI300, you cannot, because it's integrated into a single chip, you will have to monitor the power consumption of the power supply. You can actually on the node, but you probably didn't.
I would say that seems like a very bad way about making that test. I think you want to just play around with your numbers instead, and know what the power consumption of each is. But yeah, I think you need to be getting, if you're worried about power consumption, you need to be getting at least a factor of 2 speed up to make it okay, and you want more, but realistically you want more than that.
Okay. Any last questions? Yeah.
It was more of a comment on the speed up test you showed previously. There is something to be very careful about. It's that the CPU frequency will start to be throttling after some number of cores. So if you're using a single core, it will be like max frequency. If you are starting to get past the half of the core, it will start to lower the frequency. So actually the slowdown is expected even on something that will scale perfectly.
Yeah, okay.
And since you are memory bound, it's maybe not even the frequency of the CPU, it could be the memory clock that cannot follow the trend.
Thank you.
Yeah, very good point. All right, let's thank Tom again.